This video covers Generation 1 of the controller board layout. It's not my intent to get down into the weeds on the electronics. I do want to talk about why I picked what I picked and what characteristics they have. So if we start over on the schematic, the 32-bit pick is the core. This chip is designed for motor control, so it has hardware encoder processing. That was important. There are actually not that many other chips on the board. There's a programmer, there are the two CAN transceivers, prime and redundant. There is a drive chip that allows me to drive both relays on the board and external relays. And up top here is the power processing units. There is a 50-watt DC to DC converter or a 6-watt DC to DC converter. The 50-watt is used if I'm stacking a bunch of boards together and I want to run all of the boards off of one DC to DC. And the 6-watt converter is if I just want to do a standalone board for testing. Each of those DC to DCs runs two linears, one at 5 volts, one at 3.3 volts. If we go over to the physical board, there are a few things I want to point out. The first is that the prime and redundant cans have two interfaces. There are just copies of each other. There up here you have the prime encoder and the redundant encoder interface. At the top level, there are 3 UARTs, and down at the bottom, there are 2 UARTs for a total of 5. DCs go here, that's the 6-watt, the 50-watt goes here, the relays go here. And if you're wondering about these big holes that are sprinkled all throughout the board, the outer 4 are for screw mounts, and all these inner ones are basically places that if I use flying leads on, for instance, the UART, this UART here, if it has flying leads, I can route those flying leads out the side of the board, and this will accommodate a zip tie that helps take load off the soldered interface here. The idea is one board can be the master and interface, and 3 other boards can be the controllers for the steering. Now I want to go a little bit into the PIC 32 and what properties it has that made me choose it. Well, the first property is I've used it before, but I've also used a number of other ones before. And why did I pick the PIC? Pick the PIC. There you go. This is a block diagram of the whole system, and I'm certainly not going to go through it all. Over here, there is the core processor. This is what you'd call the brain, the central processing unit. On this PIC, all the other subcomponents here, the cans, down here, the UARTs, they all run independently from the core processor. That means the can operates and does what it does while the processor is running. If the main processor needs data from the can, it goes and it looks it up and says, do you have data for me? But it doesn't have to constantly pull the can to say, oh, has anything arrived? Has anything arrived? Has anything arrived? That makes programming this a lot simpler. The PIC also has a number of features that make it more robust. Here you can see there's a power-up timer, there's an oscillator startup, power on reset, watchdog timer, brownout reset, and deadman timer. I've never actually used the deadman timer. But the idea is that if something interrupts the system, if your software is screwed up and it goes to some null address and doesn't know what to do, you'll trigger the watchdog timer. If there's a blip in the power, there's a power reset. On startup, there's an internal oscillator. If it fails to start oscillating, the startup timer kicks it off. All of these things mean that that the chip is very reliable. Only if you actually fry it is it going to stop working. On the right side is a characteristic of the PIC. It's probably on other chips too, but it makes laying out a board much simpler. Let's say you had this PIC processor up here, and it would be convenient if all of your serial outputs were on the top of the chip, right? This, what they call peripheral selection, allows you to say, okay, I can route different functions to different pins on the chip. As an example, in this case, there are 24 possible functions that can be routed to, I think there's 11 of these pins. So if you wanted U3RX, that's UART3 receiver. If you wanted the UART3 receiver, you could route it to any one of these 11 pins for convenience. If you wanted the home location for this encoder, you can put the home location in any one of these 11. You can put the C3RX is CAN3 receiver. You can put it in any one of these locations. So you can sit down and lay out your board and say, what is most convenient for my peripherals, and how am I going to lay out the board so I don't have a ton of wires that are crossing over each other, or I don't have high-speed wires that are crossing over power wires. Gives you a lot of freedom. Next, I want to have a little bit of information provided about the difference between the serial and the CAN. So the serial is old, and I love serial. It's so easy to implement, but it does have some limitations. The idea on the PIC is that you have 8 bytes of transmit and 8 bytes of receive buffer. So you stuff stuff in the 8-byte transmitter, it gets automatically shoved into the transmitter hardware, comes out on the other chip, the transmitted stuff comes in and gets stuffed in your receiver. And that allows you, if you're just sending 8 bytes, it's simple. You stuff it in, it shows up here, and then you pull it out whenever you want. If you're sending more than 8 bytes, you have to make sure that you don't allow these buffers to overflow. Then you lose information. CAN is designed very differently. In a CAN bus, all of your chips sit on the same bus. They all see the same information fly by them. There are filters and masks, and the idea is that as data comes in, and CAN bus data is 128 bits of a package that holds up to 8 bytes of data. It comes in, and these storage locations, these FIFOs, I actually think of them as mailboxes. This is a mailbox that can hold up to 32 messages. So the data comes in, and the CAN module says, oh, that's for mailbox 8. And do we have a mailbox 8? And if one of these FIFOs is labeled mailbox 8, it takes the message and it stuffs it into the message buffer. Now that message buffer can be up to 32 messages deep. If another message comes in, it just shoves it in, and it's a FIFO. You can do some very nice things with this type of system. You can dedicate different mailboxes to different commands. You can exchange information between chips. And I do that on my design. So say chip 1 takes all of its local state information, packs it into 8 bytes, and sends it out on the bus. And that ends up in a mailbox of other chips. Those other chips know that if something ends up in their mailbox, they take it and they send it right back out on the bus. That way, if the chip 1 fails, when it reboots, one of the things it does is once the can comes up, it listens to see if somebody is broadcasting its own state information. If somebody is, it can take that state information and recover near instantly to exactly where it was before. That allows the system to be very robust. And the fact that you have 16 mailboxes of 32 messages deep allows you to do that. Finally, a little bit of math on the performance or the necessary things you need to do to upkeep the serial data. So the serial runs 115.2 kilobaud. That means a serial 1 byte, if you're on the serial port and you're getting 1 byte, it can fill the slot in the buffer in about 70 microseconds. If you wanted to do things super simple, then you could check that arriving buffer very quickly, and once a byte arrives, you say, okay, I'm going to process that byte one at a time as it comes in. That's kind of easier if you're sending long messages. You don't have to sort of slice things up and say, oh, I got 5 bytes. Now I have to figure out how to combine this with the other bytes to see if I have a full message or not. Or, oh, I've got 6 bytes and that's part of one message and part of another message. Looking at them one at a time makes things easy, but it's computationally expensive. 6 bytes, there's actually an interrupt that allows that you can set that goes off in a pick once you're 3/4 full. If you wait and something delays your going to check the serial input, you can overflow, and if you overflow, you lose data. CAN, on the other hand, is a 128-bit frame that has 8 bytes of data. It arrives at 256 microseconds, so significantly slower than 1 byte of serial, but you also have 32 messages in each mailbox, which means that you don't lose anything. You can go in and the full message is there, and you can process them at your leisure, well, relatively at your leisure. You can also spam messages across multiple mailboxes. I didn't have to do that. I've had to do that before, so that on something that had really long computational times, to get the service time to be much longer. I don't have to do that. I have no compunction to think that I'm going to have to do that here. I've run things like this before, and it's just not that difficult. The processor's quite quick, and as long as you're not stupid about how you calculate things, it'll work. The last bit of math here is for the encoder. 8192 pulses per rev. The 30 megahertz hardware interface handles 220,000 RPM. Obviously, that's not going to be a problem. The fastest I think my computation shows is somewhere around 600 RPM for the wheel, and so that's 6x that at the encoder. So 3600 RPM at the encoder. Not even close. Now, 8192 pulses per rev, 6:1 is the gear ratio between the encoder and the wheel. So there's 49,000 pulses per rev for the wheel itself. Obviously, we don't need steering accurate to, sub 100th of a degree. In fact, as sloppy as our system is going to be built, that's going to be impossible. If it's within 5 degrees, we're going to be fine. But we do need it for rate estimation, right? When you're spinning, the control law that I'm using requires a reasonably good rate estimator. So maximum 90 degrees in a quarter second. That's a theoretical max for what I have. That's 100,000 pulses per second. and you want it to be able to run from max down to 1% of max. That's a rule of thumb, control rule of thumb. So 1% of max is 1,000 pulses per second. And at 200 hertz processing, that's still 5 counts per control cycle min. And that doesn't sound like much, but it's quite enough at 200 hertz for the system to work well. The idea behind this design is I've sized everything and looked at everything. Hopefully, I know I've missed some things, there's no doubt, but hopefully I can get this out. I know Chinese New Year's coming up, and I need to get it put in so that I can get the boards back early enough that I can populate them and start writing code. I have a fair amount of code from the PIC32s that I have from other projects, but I need to put it all together, and there's a possibility I screwed something up. Hopefully I can fix it, but if not, it would give me another shot before the event. Need to get this thing on order.